Alright, let's talk about the universal wave equation. But before we do, let's talk about colonial soldiers. Now this fellow is from a fictitious country where their national flag is the happy face painted right on his red chest here. But you know, the colonial powers, when they were marching along and trying to, I don't know, spread whatever civilization they thought they were spreading, or take back whatever wealth they were trying to take back to wherever they came from, they got into the habit of marching around and maybe even raising their bayonets or whatever to intimidate people, and they did so in unison. And that's something I'd like to make use of. It's just a nice image. Well, maybe it's not a nice historical image, but at least it does have the idea of repetitive motion. And if the colonial powers were good at anything, it was repetitively doing the same thing to people. So here we go. We've got this gun that's going to be raised up and down as the person marches. March, 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 march. If this person is able to march and have a constant up and down motion to their weapon, regardless of how fast their feet are moving, this guy here goes up and down at the same rate. Up and down, up and down. You can imagine that if every time the gun gets up to the top of its motion, I could draw a dot. So this person moves along, 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 along. I'm going to make a dot every time I claim that he's raising his gun. So he's going to make a dot, and he lowers it and raises it, and I make another dot. He lowers it and raises it, and I make another dot. Because he's moving at the same speed, so long as he lowers and raises at a constant frequency with a constant period, as long as he moves at a constant speed, these dots would be equally spaced. But what happens if the soldier moves from one terrain to another terrain? And you know, maybe this terrain is a nice, flat terrain, easy to walk across, we don't have any troubles. Love it. Raise it, drop it, raise it, drop it. But then he gets to sort of a rough terrain. Let's say it's a sandy beach. You know, these guys always got to get into a boat or something after they do whatever it is they have to do. So we get onto this sandy beach, and things are a little bit rougher. We go slower. But at the same time, this marching fellow is raising and lowering his weapon at the same frequency. He's walking slower, but he's raising and lowering the weapon at the same frequency as he was before. Let's think about what happens now. He was going quickly. Then he slows down. The raising and lowering is going to happen at closer spacings, because he's going slower, but raising and lowering it at a uniform rate. He's physically walking slower, but his weapon is going up and down at the same frequency as it used to. I want to point out that if I could videotape this and actually trace what the tip of the weapon is doing, it might look something like this. Low, high, low, high, low, high. Oops, that wasn't very curved. Low, high, low, high, low, high, and so on. Oh, I didn't quite make that dot. But I think you see the idea. When the soldier went from one medium to another medium, I'll make that the boundary between the two media, the walking medium, if you like, something changed. It wasn't the frequency. Frequency stayed the same. He's a good soldier. He knows how to lift things and put them down at a constant frequency. And you might even say, period. Period and frequency stayed the same. But what changed? The velocity of the guy down here was fast. The velocity of the guy when he got to the rough ground, maybe it was sand, was slow. So speed decreased. Okay, fair enough. At the same time, though, the frequency stay the same and the period stay the same. And let's talk about the wavelength, because this would be sort of the distance action, or position axis, or time axis if you like. This would be a wavelength from identical portion to identical portion. And this would be the wavelength over here from identical portion to identical portion. While the speed decreased, let me get that right. The speed decreased, the wavelength also decreased. So lambda wavelength bigger, lambda smaller. Wavelength decreased. So we might say that somehow the speed is proportional to wavelength. That doesn't mean dependency. But what people do say is that speed is equal to distance over time. I believe that. We talked about that in terms of kinematics. But you know what? The distance that a wave travels is actually, could be described in terms of lambda. And the distance that it travels, as described in terms of lambda, occurs in the amount of time that we call the period. So it might make sense, instead of saying v equals delta d over delta t, for waves it might make more sense to actually say, I'll rewrite it over here nicely, v equals lambda over period. Actually, that makes a lot of sense. It all comes from the colonial superpowers. Well, thank you very much for that, at least. The other thing that we remember from once before is that period is equal to 1 over frequency. That hasn't changed. But if I sub this equation into this equation, we end up getting v equals lambda times frequency. It's really just, a rejigging of the exact same equation. But these guys are really just different forms of what people commonly call the universal wave equation. I want to make sure that people get this, though. The frequency did not cause the speed to change, and the wavelength did not cause the speed to change. It was the change in speed that modified the wavelength, and the change in speed did not modify the frequency. That's the way this relationship is set up. You're not changing the speed just because you're changing how fast you move your rifle up and down. That's just silly. And it's true for waves as well. In fact, waves are often, like for example, vibrating particles. And just because I yell at a fish, maybe this is one medium, if I yell at a fish by vibrating the particles, actually it would be vibrating the particles, it would be a longitudinal wave, the frequency of vibrations, as those air particles bump up against the change in media from air to water, the frequency of the vibrations doesn't change. In fact, the air particles would jiggle back and forth at the same frequency that I modulate my voice at. Fine. Woo! If I make that noise right over a bit of water, that same frequency is going to get transmitted into the water. But what changes is this. The speed of the transmission changes in water. Not frequency, speed changes. And when the speed changes, if the frequency doesn't, the wavelength changes. So I'm not going to be able to yell at a higher frequency underwater, but the wavelength of the waves that I make will be a different size. Thank you very much. Oh, maybe we should do an example with this, just for fun. It's not complicated. Find the speed of a wave with, a frequency of 4.0 hertz and a wavelength of 2.5 meters. You solve it. 1, 2, 3. Do you have the answer yet? Okay. Here it is. V equals lambda f. I'm looking for the wavelength, so lambda equals V over f. And if I sub in my values, V was equal to, oh nuts, what was I thinking? I got sidetracked there. I was looking for the speed. I don't have to rearrange anything. V is equal to lambda f, 2.5 meters times 4.0. And instead of saying hertz, just to emphasize a units point here, I could say 4.01 over seconds, because 2.5 times 4 is going to give me, anybody know? Exactly, 10. And then the units will be meters times 1 over seconds, which is meters per second. Beauty. If you have a question, just ask.